And the idea is to talk about excess of matrices, that a very similar concept that I introduced soon was defined by Schmidt in 1973. And this is related to counting how many ones has a Hadamard matrix. How many ones can have a Hadamard matrix, and there are many, very interesting results about that. But on the other hand, in parallel, it was a notion of quantum non-locality developed by Bell in 1964, which is in principle is very different from the notion of excess of matrices. But there are some aspects of this theory in quantum non-locality that are very much related to excess of matrices. And the intention of this talk is to establish a bridge between these two areas. And it is very nice to see that there are many people in the audience that are used to work on excess of matrices, and others are familiar with quantum non-locality. So along the talk, some people will cross this bridge from left to right, and others from right to left. And hopefully nobody will fall down in the middle. So let me start with the idea of Schmidt, which is the following. So he asked, what is the maximal number of ones that can have a Hadamard matrix of order n, where the weight, which is the call of this number, is the maximal number, is the number of ones that can have a Hadamard matrix. A bit later, Best introduced the notion of excess, which is very similar to the weight, but he considers the sum of all entries of a Hadamard matrix. So it's the number of ones minus the number of minus ones. And this is much more convenient in an operational way. So many analytical results can be derived. So for instance, here in equation 1, we have an upper bound and a lower bound for the maximal sum of all entries of a Hadamard matrix of order n. For instance, if you have a Hadamard matrix of order 2, the maximal number, the maximal sum of entries that you can have is 2, and is achieved by this matrix, for example. And this maximal number is strictly smaller than the upper bound formed by Best. But on the other hand, if you go to order 4, you can define this Hadamard matrix, the circulant one, and the sum of all entries is 8, and this is exactly the upper bound. So for some others, you can achieve the maximal value, the upper bound, and sometimes not. And this answer, the answer about when do you achieve this maximal bound for Hadamard matrices was fully solved by Best. That I will show you soon. But let me show you that there are many papers about excess of matrices along the years, and also some extension, not only working about Hadamard matrices, but also to complex Hadamard matrices, tensors, orthogonal designs, and others. So the saturation of the upper bound formed by Best is achieved if and only if the Hadamard matrix is regular in the sense that it has constant sum row, the constant row sum. And for other classes of matrices where this upper bound cannot be achieved, there are some results in the literature. For example, this one, if you have a skew symmetric Hadamard matrix of order 0 modulo 4, or a conference Hadamard matrix of this order, then there is a Hadamard matrix of this order n, which note that this is not a square, n is not a square, so if n is not a square, you cannot have a regular Hadamard matrix. Then the maximal excess takes this form. So in this way, there are many results, many classes of matrices where it is known how to construct matrices saturating the upper bound. And also this one, for instance. If you have conference Hadamard matrices, then you can establish this upper bound. So when the conference matrices have this order between these two bounds, then you have this upper bound, and it is known exactly when you can saturate this bound. And these results, you will see that are very interesting from the point of view of quantum mechanics. Also here, in this very long table, there is a very careful study about the value of excess for all Hadamard matrices, classes of Hadamard matrices existing up to order 1000. So there are 3 bounds. So here they have 3 bounds and some values found and the known value of excess, and sometimes they saturate the upper bound and sometimes not, but there is a lot of information about when can you saturate the upper bound and when you cannot. So this was a very brief summary about excess, and now let me connect this idea with Bell inequalities. But first, let me have a very soft introduction to Bell inequalities. And the very beginning of quantum non-locality, it was motivated by this paper. This paper published in 1935. This is a very famous paper published by Einstein, Podolsky, Rosen, where the title is "Can Quantum Mechanical Description of Quantum Reality Be Considered Complete?" And in this paper is one of the attacks from Einstein to quantum theory, because as many of you surely know, Einstein didn't like the quantum mechanics, especially the probabilistic aspect of quantum theory, and also the uncertainty principle, because for Einstein, nature is not probabilistic. And if you go to the lab and you cannot measure some quantity with precision, it's a problem of you, not a problem of nature. So Einstein wanted to reflect this fact in a physical theory, and quantum mechanics was in conflict with these deterministic ideas. So this is one of the attacks that he has. And in this paper, they carefully introduce the notion of element of reality. So what can be assumed that is an element of physical reality? So what is physical and is not an illusion of the observer? So if you, without any way disturbing a system, can predict with certainty, so with probability 1, the value of a physical quantity, then there exists an element of physical reality corresponding to the physical quantity. So this is a very clear way to define what is a physical quantity and what is not. But what is the problem? In quantum mechanics, when you perform a measurement over a quantum system, you are perturbing it. So it's not simple to show that something is an element of physical reality. But the authors had an idea, because they consider a bipartite system. So you suppose that you have two subsystems connected, and you prepare a quantum system in such a way that you know the relative position of the two systems with certainty. So if you know the relative position of the subsystem, and if you implement a measurement of position of the system A, then you are not perturbing in any way the subsystem B. But given that you know exactly the relative position and the position of the subsystem A, then you will know with certainty the position of the second subsystem. So you can certainly affirm that position of this subsystem B is an element of reality. In the same way, you can prepare the system in such a way that the total momentum of the system is known. And in the same way, if you measure the momentum of the system A, then you are sure what is the momentum of the system B. So momentum is an element of reality of the physical system. And moreover, these two observables, the relative position and the total momentum, can be simultaneously measured. Why? Because they commute. So position and momentum of XA and PA do not commute because of the uncertainty. We have an uncertainty principle. And the same for XB and PB, but relative position and total momentum commute. So there is a conflict here. And why there is a conflict? Because quantum mechanics does not allow you to know position and momentum of this system B with certainty. But these are two elements of reality. So quantum mechanics does not allow you to know the value of those elements of physical reality. Then quantum mechanics is incomplete. So this is the conclusion of the paper. Incomplete, but correct, because every prediction established by quantum mechanics is correct. So the solution to this problem would be to find a most general theory contained in quantum mechanics in such a way that everything is perfectly determined by theory, and you don't have probabilities and you don't have uncertainties. So this was the idea of Einstein, Podolsky, Rosen that didn't catch too much the attention of the community until somebody else came up 30 years later, which was John Bell. John Bell published this paper in 1964, and it's about on the Einstein-Podolsky-Rosen paradox. So what was the idea of Bell? So Bell tried to prove that quantum mechanics, he was proving that quantum mechanics is not a theory compatible with this idea of Einstein. So how can you do that? So you can consider, for instance, correlations, because when you go to the lab, if you have two systems, you can measure correlation between these two systems. And if you assume the idea of Einstein-Podolsky-Rosen, so if you assume that there is a more general local hidden variable theory, so a physical theory where some variables are hidden because you don't have access to them, but they exist, and everything can be determined with certainty in nature, then these correlations associated to measurements implemented to two parties, A and B, have to be equal to the product, because the correlation of the product, if you have a local theory, is equal to the product of correlations because of locality. But also, if you assume determinism, then the expectation values are always the same. Yes, because if you implement an experiment in a deterministic theory, you will always obtain, if the state is prepared in the same way, you will obtain the same value. So all the expectation value coincides with the value that you want to observe. And in quantum mechanics, the values that you observe and the eigenvalues of your observables. So these AI and BJ are quantum observables, are physical observables. And then you have these quantities represented by some numbers AI and BJ, and they represent the value that you observe in nature. On the other hand, if you assume quantum mechanics, then you have to take this rule, which is the Born rule, and the expectation value is given by this trace of this product, where you have the observables. Here should be A and J. And this is the quantum state of your physical system. The problem, there's a small problem here, because if you want to prove some kind of contradiction between a local hidden variable and quantum mechanics, you cannot just consider correlations, because no correlation, no single correlation will find a contradiction. But if you consider linear combinations of correlations, then you will find something. For instance, if you consider this correlation, let's assume that now your physical observables have only two outcomes, and let's call them +1 and -1. Then in a local hidden variable theory, if you consider this linear combination, all of these will be numbers +or-1, and you have to take the maximum over all possible combinations of +-1, like this rule. And it's simply to realize that the maximal number is 2. But on the other hand, if you take the same expression, but you consider the expectation values according to the quantum rules, and you optimize over all possible quantum observables and over all possible quantum states, you find that the maximal value is 2 square root of 2. So it's larger than this value. So how is possible to have a larger number if you consider here the maximal number over all local hidden variable theories? So this means that quantum mechanics is not in agreement with a local theory. So quantum mechanics is a non-local theory. This is the main result of the paper of Bell. And since then, it was developed a very important theory about quantum non-locality, and there are many results and practical applications, and it was shown that quantum non-locality and entanglement are inequivalent resources, so they can be applied to different practical applications. So for instance, Bell inequalities are very useful to implement device-independent protocols. So you can implement some practical protocols without relying on without having to trust on your measurement apparatus. So if you obtain some certain values for this, for example, if you implement an experiment and you achieve this 2 square root of 2, there is only one way to obtain them, and this is when you have some specific measurements at some specific quantum state. So you don't need to rely or to trust on your measurement devices. So how can you obtain this local hidden variable value? So it's the maximum over this quantity. And this local hidden variable value is also sometimes called the classical value. And here there is an H for some reason that you will see very soon, because this maximum number can be organized in this way. I can think that these 4 numbers are organized in a square 2 times 2 matrix in this way, where you have the sum of all the entries. But also this can be written in this way, where you have the Hadamard matrix of order 2, 2 diagonal matrices where you have A0, A1, and B0, B1 in the diagonals, and then you maximize over these quantities. But this is fully equivalent to the notion of excess, of maximal excess. So this is the maximal excess of all Hadamard matrices of order 2, which is equal to 2, as we found some minutes ago. So this is the connection between the excess of Hadamard matrices and the way to calculate the classical value of a Bell inequality. So excess has nothing to do with the quantum value, but it's very important to calculate the classical value. And as we will show later, one of the most important properties of Bell inequalities is to characterize what are the so-called tight Bell inequalities, and that I will show you later. And this relies only on the classical value. So you can study excess of Hadamard matrices and try to find tight Bell inequalities, which are the most important Bell inequalities. Now let me show you the results. So the first results the first result is the connection between the classical value and excess of matrix, what I already shown. And why should we care about this? Because these two theories, the quantum non-locality and excess, were progressing in parallel. And from the mathematical point of view, there are many results about excess which are not yet known in quantum mechanics. So there are many results to apply to quantum mechanics taken from the literature of excess theory. So let me show you another result, which is an upper bound that we found. So suppose that you have a matrix of order n that already has the maximal excess. Here I mentioned with respect to Q equivalence, but in this talk I am restricted to Q equal to 2, where the notion of equivalence is exactly the same that the notion of equivalence for Hadamard matrices. So whenever you say equivalence or Q equivalence, I mean that you can interchange columns or rows of a matrix or multiply by minus in columns and rows. Then the upper bound for this classical value, when the matrix has maximal excess, this is very important, is upper bound by n times the numerical radius of the matrix. And why this is interesting? Because the numerical radius is upper bound by this quantity, which is the spectral radius, and lower bound by the singular value, maximal singular value. And this observation is related to a result known in quantum mechanics, which established that the quantum value is greater or equal than the classical value, is upper bound by n times the maximal singular value. So if you merge these two inequalities, if you consider that this classical value is lower or equal than the quantum value, then you find something that's very much related to the best bound. Because if you assume that M is a Hadamard matrix, then the maximal singular value is the square root of n. So this is just reflecting this result of Pell. So the maximal excess of a matrix is smaller or equal than n times square root of n, or the maximal singular value of a Hadamard matrix. So here we see that some things are matching with the result from excess. Another result that we found is the following upper bound for the classical value, which is in some sense is similar to the upper bound found by Best, but here we have square root of n times some number which is a function of the entries of the matrix. Sorry, I didn't say what kind of matrices are M. We can assume that M is any real matrix for the purpose of this talk. So let's assume that M is any real matrix. So the sum of entries is always real. And this upper bound is saturated if and only if M is a constant row sum matrix. So this goes in the same way that the upper bound found by Best. So the only matrices that saturate the bound are those having a constant row sum. And in such case, of course, the maximal excess is given that by n times the value, this value gamma, which is the constant row sum value. And when M is a Hadamard matrix, this upper bound reduced to the result found by Best, because this number is exactly n. Okay, now let me tell you what are the most important Bell inequalities. So these are the tight Bell inequalities, and why are they important? So it turns out that all strategies which are compatible with a local hidden variable theory form a polytope in the correlation space. So you have a polytope, which is here denoted by L. This is a polytope in the space of correlations. So it's bound by some hyperplanes. And outside this polytope, you have some correlations which are not in agreement with local hidden variable theory, like for instance, what I was shown later with this value of 2, square root of 2, which is saturating the, it's overpassing the maximal value, achieving a local hidden variable theory. And precisely what happened in this situation is that we consider an hyperplane, and the correlation which achieves this 2 square root of 2 value is here. So you achieve a value which is larger than those allowed by this theory. So it's very important to characterize the border of this local hidden variable polytope, and the border is given by all tight Bell inequalities. So the hyperplane which are the borders of the local hidden variable polytope. So how to determine this tightness? When a Bell inequality, when a given Bell inequality is tight. So there's a very simple recipe. You have to find all optimal local hidden variable strategies. What I mean by all optimal local hidden variable strategies, so you have to find all the values, all plus minus combinations here, such that you achieve the maximal value allowed in quantum, allowed in a local hidden variable theory. For instance, in the example that I've shown before, this will be equal to 2 when you consider the Hadamard matrix of order 2. So this is equivalent, if you think in a mathematical way, this is equivalent to take a Hadamard matrix of order 2 and ask in how many ways you can multiply in rows and columns by -1. Permutation doesn't matter because it does not modify the value of the sum. So in how many values you can multiply by -1 in rows and columns in such a way that you obtain the maximal possible excess. So you collect all these plus minus values, you arrange all of them in a vector which has order m squared, where m is the order of this matrix. And then what you have are all the points in a phase of this polytope, because all strategies saturating these inequalities are in the surface of the polytope. So you have all points of a phase, but the question is whether this phase is a facet, so a phase of maximal dimension. So if you are in dimension m squared, the maximal dimension of a hyperplane is m squared minus 1. So you have to determine whether all these points are affine linearly independent. How many of them are affine linearly independent? So if you get m squared, sorry, here should be a square. If you get m squared minus 1 affine linearly independent points, then you have a facet. And for instance, the CHSH inequality, which is the inequality related when you consider the Hadamard matrix of order 2, is tight. So it is a facet of the polytope. So it's very interesting that you have a facet when you consider a Bell inequality, Hadamard matrix here. So when we observed this very well-known fact, we asked whether higher orders Hadamard matrices are also determining tight Bell inequalities. And we found these results. This is the number of measurement settings, which is equal to the order of the matrix. So we think that we have Hadamard matrices of order m. And for all these orders, we have these results. So this is the number of vertices, and this is the number of affine independent vertices. So sometimes we achieve this m squared minus 1, and sometimes not. So for order 2 is tight, order 4 is not tight, but order 8 is tight again, 12 is tight again. For order 16, there are 5 classes of Hadamard matrices. So we study all of them individually, and 3 of them are not tight, but 2 of them are tight. And for order 20, all the classes define tight Bell inequalities. This is very curious. And it's even more curious if you take into account that those where tightness is not achieved, the classes are represented by regular Hadamard matrices. So Hadamard matrices where you have constants on row. And this is very interesting also from the point of view that if you recall the best bound for regular Hadamard matrices, the classical value, so the upper bound for the excess, which is equal to the classical value, achieve the upper bound of the classical value, which is also the upper bound of the quantum value. So in this way, the classical and the quantum value saturate the upper bound. So there is no quantum advantage. And there is a very famous open conjecture in quantum mechanics, in quantum non-locality, which establishes that if you have a bipartite, so if you have 2 parties involved, every Bell inequality having no quantum advantage is not tight. And this is reflected in this result. So it will be very, very interesting to prove in general, somehow, that for any Bell inequality related to a Hadamard matrix, which does not belong to a class of regular Hadamard matrices, forms a tight Bell inequality. So this is a conjecture that we established in our paper. On the one hand, perhaps this is not simple to prove because Hadamard matrices are not characterized in infinitely many dimensions, for infinitely many orders. But I think that this doesn't matter because this fact, I think this fact of tightness should be reflected in something relying at the very heart of Hadamard matrices. So I think this property, I believe this property can be demonstrated in general only using very fundamental properties of Hadamard matrices. It doesn't matter if you don't know the Hadamard matrix of order 664 or any other. So this is, I invite you to join some of you if you want to attack this problem, which is highly interesting. And in the future, we will try to prove this result, which is not simply, which we already tried to find it, but in some way it should be possible to do it. So to summarize, we established a connection between the mathematical notion of excess and the classical value of bipartite Bell inequalities. And this bridge allows us to take advantage of a large number of results known from the theory of excess, studied by many mathematicians along the last 40 years. And also inspired by Bell inequalities, we extended the notion of excess to any real matrix in this talk, but in our paper, we also consider certain classes of complex Hadamard matrices satisfying some symmetry, which also has real excess and real maximal excess. And we derive some upper bounds similar to the best bound, which hold for the local hidden variable value, thus fully characterizing the saturation of one of them. And finally, we conjecture that any Hadamard matrix of order n, not equivalent to a regular one, produce a tight Bell inequality with n settings and 2 outcomes. So that's all. Many thanks for your attention, and I invite you to have a look to our paper. And also, I especially invite you to write an email to us and show your interest if you have it. So we are very happy to extend our collaboration to mathematicians.